Hello students, today we are going to discuss matrix method in paraxial optics. Before going into that topic directly, we need to discuss a simple consideration that is called paraxial paraxial approximation. Okay, so what happens under paraxial approximation? You see, whenever you face a lens, okay, so my diagram may not be perfect, so please excuse me for that. So suppose that there is a ray of light coming from a particular object, okay, and you may have a set of rays like this, okay, so you are expecting a image here. And similarly there may be few rays if it is an extended object, okay, if it is an extended object, okay, extended object, opposite means point object. So if it is not a point object, that means if it is an extended object placed in front of a lens, then what happens, you can expect different kinds of rays. So some of the rays may be coming like this also. So when they pass through the lens, they may meet here, okay, so you can understand. So there are this kind of rays which are away from the principal axis. So this middle one is the principal axis, or you can say the optics axis of the system, okay, principal axis. So the rays which are away from the principal axis are called peripheral rays, okay. So they make this kind of rays, you see, they are making a big angle, okay, with the principal axis, but there are a set of rays which are very close to the principal axis. They are called paraxial rays, okay. So paraxial rays, these are the rays which make very small angles, okay. So if I consider this angle made by the paraxial ray with the principal axis is very small, okay. So that means in under paraxial approximation we consider only those rays which are very close to the principal axis, or in other words we can say that we can consider only those rays which are making small angles with the principal axis. Small angles means theta will be very small. So as usual, mathematically sin theta means theta, cos theta means 1, so tan theta is equal to what? Sin theta by cos theta, that means it is equal approximately theta. So these are the three things that are coming under the paraxial approximation. So throughout this syllabus of optics, mostly we will be considering the geometries under geometrical optics under paraxial approximation, okay. So that is the first thing. Now let us discuss about what is a matrix method. Suppose that you have a lens like this, okay, and convex lens. So convex lens, so this is a converging lens. So let us draw the principal axis. This is a principal axis. So there is an object nearby and the rays of light are coming like that, okay. And what happens is a converging lens, so you will get the image here. So this is a point image I1, okay, I1, fine. So this is the position of the image of an object placed on the principal axis. Now suppose that you have a complicated system. This looks a very simple system, isn't it? This is an optical system, but it contains only one lens. But if there is an optical system which contains more than one lens, then what will be the situation? So for that, suppose that this ray I am removing, and suppose that, okay, let me remove this also. So earlier the image we found here, isn't it, I1, okay. So now let me put a lens here, okay. Suppose this is a converging lens, okay. So what happens after that? So ray of light will definitely be this is a diverging lens, 2 is a diverging lens, so it's a concave lens, okay, diverging lens. So this ray will come like this, okay, and since this is a diverging lens, 2 will diverge the ray of light like this, isn't it? So you see, initially with one lens we got the image here, but with two lenses, are we going to get the image here? Is it possible to get the image here? No, the image is not here. So what's wrong then? Suppose simply this dot represents the earlier position of the image. So to get the image, what we need to do? We need to put another convex lens here. Okay, so it comes like this, and it goes like this. So you can see now the image is here. So let me tell it I2. Okay, so initially we got the image here, but where we had a complicated system, so we had 3 lenses. So now we have got the image here. Okay, and initially it was I1, now it is I2. That means you can understand that when you have an optical system, see, this whole thing is an optical system. Earlier it was an optical system with only 1 lens. Now you have an optical system with 3 lenses, and now images is different. Okay, so imaging, okay, so what is that? Imaging with a complex optical system is complicated. Okay, complicated. What happens, you see, initially with this lens only, okay, the image we obtained here only. Alright, this dashed line. Now when we put another this lens, okay, when we have put this concave lens next to one, then what happened? Now these rays are behaving like the object now. Okay, now earlier it was a incident ray, and it was a refracted ray. Now this ray, now refracted ray, but for this lens these rays are behaving like, the rays coming from lens 1 are behaving like incidence ray. Okay, similarly for this lens 3, the refracted rays coming out of 2 are behaving like incident rays. Okay, so we have so for every set the perspective is changing. I have mentioned in the theory, you can check it. So for the lens 2, the rays, refracted rays coming out of 1 are behaving like incidence ray. Similarly for the lens 3 also, the refracted rays coming out of 2 are behaving like an incident ray. Okay, so we need to change the perspective with respect to every lens. So we need to change our strategy with respect to every lens. That means it's a complicated process. We need to find out the image step by step. So this is our first step, this is the second step, and this is the last step. Okay, so it is a complicated thing. So when you have, but we are talking about only 3 lenses, 1, 2 and 3. What happens if you have a set of lenses like 10, 20, 30 lenses? Then it will be this process will become very tedious. You can't do it in one step. So for that there is a requirement of developing a particular technique for obtaining the image. Okay, so there is a requirement of development of a technique. I am just calling it a technique. Okay, to produce, or you can say that or to calculate the position of an image from a complex optical system containing numerous lenses. Okay, so this technique is called matrix method of paraxial optics. Okay, So for that, to discuss it in detail, we will have to consider one ray diagram. So let me do that. So for that, that ray diagram will look like this. Suppose that you have an principal axis first of all, yes, and then you have a, first of all you have a convex lens, okay, and then and I will simply consider a concave lens also, okay, and suppose that a ray of light is coming like this, okay, and I will consider 2 points. Suppose this is the point P, okay, on the ray, and I will consider another point, say I will call M, okay, and I will drop some perpendiculars like this. This is a ray of light, okay. I am marking by arrow, or whenever you draw ray diagram, you must show the arrow. If you don't show the arrow in the ray of light, then it is totally meaningless. It will not be considered as a ray diagram. Be careful about that. So I will draw one more perpendicular. So say this is PP dash, this is MM dash, okay. So let me name this height as x1 and that this height to be x2. So this is x2 and this height to be x1. Now so you can see that this is the principal axis, the middle one. This is the, I will name it, say let me name it as capital X and capital Y, okay. XY is the principal axis. Now see that this ray of light at the point P, okay, is making an angle. Suppose that, let me name it as alpha 1, and the similar ray of light at M is making an angle alpha 2 with principal axis, okay, and the point at which it strikes the lens L1, I will name it as Q, okay, and this axis, although I said XY, let me remove it. I will not say it XY, it will be very confusing. So I will consider rather like an coordinate axis, okay. So I will consider it as, X, Y, Z. So this is nothing but Z axis, and this direction is nothing but X axis. If something is there on this direction, it will be Y axis. I hope you can understand that, okay. Now suppose that this distance between these arbitrary points, you might be thinking, what are the points P and M? Simply we have just considered some imaginary points on the ray of light moving towards the lens L1. Now we will define something, okay. What is that? Now in matrix method, in paraxial optics, we will define a particular coordinate. So we call it coordinate of the point P on the ray is, okay. Now you know that coordinate means, what do we say? X comma Y, isn't it? So here also we will have defined some coordinates. So what are the coordinates? That will be defined as xi, alpha I, okay. Now you can understand that what is x. X represents the height of the ray of light from the principal axis, because you can see that this is the x, this is also the x, isn't it? So this is nothing but the height of that ray from the principal axis. So we have named it like that, and alpha is nothing but the angle, okay. It is the angle made by the ray at that point with the principal axis. So I will tell you again. So x is a height of the ray of light at that point above the principal axis, and alpha is the angle made by the ray of light at that point with the principal axis. Whenever I am saying at that point, that means what is the coordinate, at which point you are going to find out the point, coordinate. So here the point is P. Similarly, if somebody asks you that what is the coordinate of the point, what is the coordinate of the point M? Okay, so then what will be that? What is the height of M? It is x2. What is the angle made by M? That is alpha 2. So it will be written as x2 comma alpha 2. For P it is xi comma alpha I, x1 comma alpha 1. Okay, so the xi alpha I have written as a random generalized number. Okay, so instead of specifying angle made by the ray of light with z axis, so we can specifically specify a particular quantity. So we can further specify a quantity lambda. Okay, so what is lambda? It is basically equal to n sin alpha. Okay, so n sin alpha. So here what I will do, look at this diagram. See, this angle is called alpha, isn't it? This angle is called alpha 1. So I will call this angle as psi. Okay, so I will call this angle as psi. So you can see that alpha 1 is nothing but 90 minus psi 1. I will name it psi 1. Okay, so you have, so n sin 90 minus psi 1. So if I have lambda 1, okay, so n is the refractive index of the medium, so it will be cos psi 1. So lambda 1 is equal to, say it is n1 I am giving. So similarly, if you have lambda 2, it will be n2 cos psi 2. If you have lambda 3, it will be n3 cos psi 3, like that it will go on. Okay, so this particular thing, lambda equal to n sin alpha equal to n cos psi, is a very important quantity that is called optical direction cosine. So you need to write it as optical direction cosine. Okay, ODC, this term. Okay, this lambda equal to n cos psi is called optical direction cosine. So you may be asked in examination that define optical direction cosine. So what should be your answer? That optical direction cosine is nothing but the product of the refractive index of the medium with the cosine of the angle made by the ray of light with the x-axis. So what is psi? Angle made by the ray of light with x-axis, because you know that principal axis is nothing but z-axis. So when I have defined this as height of the ray of light at that point above the principal axis, that means above the z-axis. Okay, this is also the z-axis, but when it is about alpha it is z-axis, when it is about psi it is about x-axis. So that thing you should keep in mind. Now the thing is that you can see in this diagram, let me go back to this diagram. Yes, Now in this diagram you can see that whenever the ray is propagating, okay, throughout this optical system, the ray has first when transferred through this, yes, certain refractive index medium, okay, then the ray will enter into this material, isn't it? So it will be refraction, and again it will transfer through this, and then again it will enter through this, so it will be again refraction, again it will transfer through this. So throughout this process we have two types of processes going on. The ray basically suffers two types of things. What are the two types of things? I will show you. Okay, so when the ray is going from here to here, okay, here to here, it is called translation. Means no change in the medium happens, no change in the medium, okay, no change in the refractive index. Then it passes through this lens, so that is called refraction, that means change in the medium. Then again it passes through this, okay, then again it is translation. Then again it passes through this lens, so again it is refraction, that means change in the refractive index, change in the medium. Then again finally to keep the image it passes through translation. Understood? So you can understand that throughout this process the ray of light is going through basically two types of changes. One is called translation and another is called refraction, okay. So it can occur in number of times, okay, it depends upon how the lenses are kept in the optical system, but it happens. So in an optical system you can't have single refraction or single translation, it will always be a combination of both. So that means we have got that whenever a ray of light propagates through an optical system, it undergoes two types of operations, okay. First thing is called translation, and next thing is called refraction, okay. So basically translation means it happens in a homogeneous medium. I told you what is a homogeneous medium, means where there is no change in the refractive index, and refraction basically occurs when there is a change in the refractive index. So here it is a change in refractive index, or you can say the change in medium. So it means both the things, okay. So translation means it is homogeneous, there is no change in the medium, okay. Now in the next video we will discuss what are the effects of translation, and then what are the effect of refraction, and how do we convert into the matrix method. That thing we are going to discuss.